Section 1. The most famous number in physics, we all think we understand the speed of light. It is the most famous number in physics, repeated in classrooms, documentaries, and late-night debates. 299,792,458 meters per second. A cosmic speed limit that nothing can outrun. It sounds straightforward, almost mechanical. Something moves, light moves faster. But that assumption hides a deeper problem. Speed compared to what? Exactly, speed only makes sense against something else. A reference in everyday life. Motion is always relative. A car feels fast beside a bicycle, slow beside an airplane. Everything depends on perspective. There is no universal backdrop marking absolute rest. The Earth spins, the Sunday moves, the galaxy drifts. Still, we speak of speed confidently, as if it were fixed. Classical physics agreed with that intuition. Velocity was a relationship between objects. Change the observer and the measurement changes too. Nothing privileged one viewpoint over another. There was comfort in that symmetry. The universe seemed democratic about motion. Then came an unsettling discovery. One exception refused to cooperate. With everything, light did not behave like everything else. No matter how you moved toward it or away from it, its measured speed remained the same. Chase it at half its value and it still escapes you at full strength. Turn around and it does not slow down. It ignores your motion. At first, this sounds like a technical curiosity, a strange detail for physicists to debate. But think about what it implies. If speed normally depends on perspective and light refuses to adjust, then perspective itself is being challenged. Something deeper than motion is at stake here. Something foundational is cracking. Because if light will not change its speed, then universe must change something else instead. Measurements of distance can stretch. Measurements of duration can compress. Space and time, thought independent, begin to negotiate with each other. The number we memorize starts to look different. Less like velocity, more like law, and that is where the real story begins. What we call the speed of light may not be about speed at all. It may be about structure, about the hidden rules that reality refuses to break. If that is true, then this famous number is not measuring motion. It defines Section 2. Speed is always relative, except once before light disrupted everything. Motion seems simple. If you throw a ball forward inside a moving train, its speed depends on who is watching. To you, it travels at a modest pace. To someone standing beside the tracks, it inherits the train's motion and moves faster. Velocities stack. They combine. They behave logically. This principle governed physics for centuries. Add your speed to mine and you get a new speed. Subtract it and you get another. The universe did not privilege any observer. Whether you were standing still or racing forward, the laws worked the same. Motion was flexible, measurements adjusted, nothing resisted. Then light entered the equation. Imagine standing still and shining a flashlight. The beam races away at its usual value. Now imagine running toward that beam at tremendous speed. Intuition says the light should approach you more slowly because you are chasing it. Classical logic predicts subtraction, but experiments refuse to cooperate. The beam still approaches at exactly the same speed. Reverse the situation. Run away from the beam. It should close the gap more slowly. It does not. No matter how fast you move, no matter how carefully you measure, the result remains stubbornly identical. The speed of light does not add. It does not subtract. It does not negotiate. This is not a small glitch. It shatters the foundation of classical motion, because if velocities cannot simply combine, then something else must adjust to preserve consistency. The universe refuses to let light speed change. That means the burden shifts elsewhere. Here is the turning point. If two observers disagree about motion, but both measure the same speed for light, then they cannot agree about distance and time. One observer's second cannot be identical to another's. One observer's meter cannot be universal. To protect that single number, reality sacrifices the absolutes we trusted. This is where contrast becomes profound. For every other object, speed depends on perspective. For light, perspective bends instead. Time slows, length contracts. Events that seem simultaneous to one observer, separate for another. The world reorganizes itself quietly to keep one value untouched. And suddenly the famous number stops looking like velocity. It looks like a boundary condition, a constraint woven into space-time itself. Light is not special because it travels quickly. It is special because its speed refuses to yield. The question now becomes unavoidable. If this number cannot change, what exactly is it protecting? What structure demands such loyalty from the universe? Section 3. When time gave up its independence, when confronted with the stubborn constancy of light speed, most physicists tried to preserve the old framework. Maybe there was an invisible medium. Maybe measurements were flawed. Maybe something subtle had been overlooked. But in 1905, a young patent clerk named Albert Einstein made a radical move. He did not try to save classical intuition. Einstein began with two simple postulates. The laws of physics are the same for all observers in uniform motion, and the speed of light in vacuum is the same for all of them too. No exceptions, no hidden reference frame, just those two principles. From that starting point, something extraordinary followed. If the speed of light cannot change, then measurements of space and time must, not metaphorically, literally. Clocks tick at different rates depending on how fast they move. Rulers shrink along the direction of motion. Events that appear simultaneous to one observer occur at different times for another. Time, once thought universal and absolute, gives up its independence. Imagine two observers passing each other at enormous speed. Each carries a clock. Each insists the other's clock is running slower. This is not illusion. It is built into the mathematics of space-time. The faster you move relative to someone else, the more your experience of time diverges. This is time dilation, and it is not theoretical poetry. Atomic clocks flown on airplanes confirm it. Satellites must account for it to keep global navigation systems accurate. The bending of time is not philosophical. It is engineered into modern technology. But beneath the strangeness lies a deeper pattern. The speed of light functions as a conversion factor between space and time. It links meters and seconds the way a currency exchange rate links dollars and euros. Change your motion, and the exchange rate forces a rebalancing. Distance and duration adjust to preserve that constant ratio. Suddenly, c is no longer just a velocity. It is the stitching that binds space and time into a single fabric. What we once imagined as separate dimensions are revealed as different aspects of one structure, space-time. The famous number is not telling us how fast light moves through space. It is telling us how space and time trade with each other. And once you see that, the implication becomes impossible to ignore. If c governs the relationship between space and time, then it is not merely a speed limit for objects. It is the structural rule that reality must obey. But there's still one layer deeper to go. Section 4, the universe's maximum causality. By the time relativity settled in, something subtle had shifted. The speed of light was no longer just about motion. It had become a boundary, a dividing line between what can happen and what cannot. We often hear the phrase, nothing can travel faster than light. It suggests a race, as if particles are competing and light simply wins. That is not what is happening. The real statement is deeper. No influence can propagate faster than light. Imagine an event, a star exploding in a distant galaxy. The light from that explosion spreads outward in all directions. But so does every other possible influence from that event. Gravity changes, information radiates, cause begins its journey toward effect. That expanding boundary forms what physicists call a light cone. Inside the cone, events can be connected. Outside it, they cannot. Not yet. The speed of light defines the shape of causality itself. It is not about photons being quick. It is about the structure of space-time enforcing order. If information could move faster than light, cause and effect would break down. In some frames of reference, effects would precede causes. Paradoxes would multiply. The logical sequencing of events would unravel. The universe avoids this chaos by imposing a strict limit. And that limit is c. This is where mass enters the story. Light travels at this maximum rate because it has no mass. Anything with mass requires energy to accelerate. The closer it approaches the speed of light, the more energy it demands. The requirement grows without bound. Infinite energy would be needed to reach c. So massive objects are forever confined below it. But that confinement is not punishment. It is geometry. Space-time itself is structured so that mass follows paths within the light cone, never crossing its boundary. The speed of light is the slope of that boundary. It determines how steeply time tilts into space. Seen this way, c is not a property of light at all. Light simply reveals it most clearly. Photons move at that speed because that is the natural rate at which space-time allows causation to unfold. The number is less about travel and more about connection. It defines how quickly one event can meaningfully influence another. It synchronizes the universe, ensuring that cause precedes effect in every consistent frame of reference. And that raises the final. If this limit shapes space-time and guards causality itself, where does it come from? Section 5, not a speed but a signature at this point. The illusion is gone. The speed of light is not simply a velocity assigned to photons. It is not just the upper bound of motion. It is the signature of space-time itself, the number that encodes how reality is built. To see this clearly, strip light from the picture entirely. Imagine a universe with no stars, no glowing atoms, no photons at all. Even in that empty darkness, the constant we call c would still exist because it does not belong to light. Light merely travels at that fundamental rate. In the equations of electromagnetism discovered by James Clerk Maxwell, this number appears naturally from the properties of electric and magnetic fields. Long before relativity was fully formed, the mathematics quietly predicted a wave moving at a fixed. That speed turned out to match the measured value of light. Einstein did not invent the constant. He recognized its authority. What c really does is convert time into space. Multiply time by c, and you get distance. Divide distance by c, and you get time. It is a bridge between dimensions. In modern physics, we often set c equal to 1, not because it disappears, but because it reveals something profound. Space and time are measured in the same units once properly understood. The constant is not about how fast something moves through space. It is about how deeply space and time are fused. And this fusion reaches further still. In the iconic equation, E equals mc squared, the squared term is not decorative. It shows that mass and energy are connected through that same structural constant. The energy locked inside matter is scaled by the square of space-time signature. So when we repeat the number 299,792,458 meters per second, we are not reciting a racing statistic. We are reciting a rule about how information spreads, a rule about how cause becomes effect, a rule about how time leans into space and space leans back. Light is not special because it is fast. Light is special because it reveals the architecture. The speed of light is not about speed, it is about the shape of reality itself.